So here we look at the second part of the fundamental theorem, the integral form, the one that lets us evaluate definite integrals for any function whose antiderivative we can find. So again, it says that if f is continuous, lowercase f is continuous, at every point on the interval a to b, and capital F is any antiderivative, then the definite integral is just the difference between the antiderivative evaluated at the upper and lower limits of integration. So the proof it requires the function form of the fundamental theorem. So we're going to say, I'm just going to say start with the fact that capital F is an antiderivative, which means its derivative is lowercase f. And so, and that's just, I mean, I'm just reversing the language here. If f is an antiderivative, then its derivative is lowercase f. By the fundamental theorem of calculus, the function form, so we needed that other form in order to do this. We know that I can create a function, called capital G of x, and I can make that be the guy who accumulates area from a to x under lowercase f. I need to use a t. Right? And so by the fundamental theorem of calculus, that means that its derivative is also lowercase f of x. So now I've got two functions, capital F and capital G. They have the same derivative. That must mean they differ by a constant, right? Just like x squared plus 2 and x squared plus 5 have the same derivative, 2x, they differ by a constant. So that means capital F of x is just equal to g of x plus some constant. And so now I can just say, and so here's where I get what I want. I say f of b minus f of a, those are capitals. Well, that's just the same as g of b plus c, because that's f of b, because I just plug those in, minus g of a plus c. And you can see what's going to happen here after rearranging some terms. I get those c's to cancel, and I just get g of b minus g of a. But that's just, if you look at what g of b is, g of b, since I define it to be that integral there, it's the integral from a to b, f of x. Now that I put values in, I can put x there if I want. Minus g of a, which is the integral from a to a. But this is just 0, so I get that integral there. So I've shown that capital F of b minus f of a is equal to this integral here. All right. So I think we've already seen examples of this, but there's the proof. Let's go apply it. All right, so we have a definite integral whose exact value we now have the power to find. So we're going to do it by finding an antiderivative of x to the fourth minus x squared. So notice an antiderivative is 1/4 or 1/5 x to the fifth minus 1/3 x cubed. So I can use that to get the answer. So notice or notice the notation I'm about to use here. This is just some common notation. If I want this if I want to write in this antiderivative here, what you'd typically do is once you find the antiderivative, you'll say, okay, that's 1/5 x to the 5th minus 1/3 x to the 3rd. You draw a line because you're going to evaluate that at 1 and at -2 and subtract. Alright, so this is a common way of writing it. So that's going to be 1/5 1 to the 5th minus 1/3 1 to the 3rd. That was me plugging in 1 into my antiderivative. Minus 1/5 times -2 to the 5th minus 1/3 -2 to the 3rd. Alright, so there's negatives flying all over the place here. And the point here now is that it's just the arithmetic that we have to be careful with. But this will result in the exact value for the area, the net area under the function x to the 4th minus x squared. So this ends up being, just to finish it, that's 1/5 minus 1/3 minus the quantity -2 to the 5th is -32 over 5. That's -8/3, but then it's a minus -8/3, so plus 8/3. And so that ends up giving me 1/5 minus 1/3 plus 32/5 minus 8/3. So -1/3 and -8/3 is -9/3 and plus 33/5. So it's -3 plus 6 3/5. And that ends up giving me 3 3/5. Or in other words, 3.6. So that is the exact area there, and I'm going to put it up on the calculator so you can see that that's exactly what we get when we evaluate that definite integral. All right, and what's happening here is that's lowercase f. This guy here is my uppercase f, and so this here would be that's f of 1, and that's f of -2, and I've subtracted them. All right, so that's what it looks like notation or symbolically. So we've solved the problem. If we can find antiderivatives, we can evaluate definite integrals. Let's return to problems whose answers we know, but let's answer them using the fundamental theorem. So this says find the area of the region between y equals sine of x and the x-axis on the interval 0 to pi. So again, that's this region here. We know that's 2 because we've been doing it all along with the calculator. Now let's show that that's 2. So that area there is the same as the integral from 0 to pi of sine of x dx. The antiderivative of sine of x, so that's what we need to do to get this exact answer. The antiderivative of sine of x is negative cosine of x. And we're going to evaluate that from 0 to pi. So that equals negative cosine of pi minus negative cosine of 0. Be very careful with negatives. This first negative is the subtraction from the fundamental theorem. That second negative is from our antiderivative. So this is negative, the cosine of pi is -1, minus the cosine of 0 is 1, so it's -1. So now I've got -1, which is 1, minus -1, which is a 1. So I've got my 2, and there we have it, the exact answer. We know furthermore that if I just continued that integration and went all the way to 2 pi, I really should get 0, right? Because that's going to be 2, and that should be -2. So it should be 0. Let's just confirm that that happens. So I take the integral from 0 to 2 pi, of sine of x, which again we know has antiderivative negative cosine of x from 0 to 2 pi. So that equals negative cosine of 2 pi minus negative cosine of 0. Cosine of 2 pi is 1, so it's negative 1 minus negative cosine of 0 is negative 1. So that's negative 1 plus 1, which is 0, which is what we'd expect. So it's great that our theory is confirming what we already know, and that's how you know you got a good theory. Alright, so there's the fundamental theorem of calculus, the integral form. You're probably going to need a lot of practice on this, so make sure you get it in so that you can apply this theorem consistently every time.